This is the final examination of Xinyu Liu for the degree of Doctor of Philosophy in Computer Science. The candidate has satisfied the course requirements for the degree of Doctor of Philosophy in Computer Science. The candidate now appears for the final examination on the thesis entitled Robotic Language Grounding Through Structured Representation Towards Robots That Use Natural Language. So I'll just say a few words and then I'll give it to you to take it away. So Jason was the first, one of the first students of my second round of PhD students. So he joined my lab 6 years ago. 2018. Yeah. That's better. Doesn't that sound better? In 2018, and he did some of the coolest papers that I thought have come out of my lab in the area of language understanding. In particular, I think the Lang to LTL paper that goes from English to linear temporal logic was a really significant advance both in how we were thinking about language understanding and also in terms of how the field was thinking about it, because we were like using LLMs, but we weren't like throwing the baby out with the bathwater because we were still relying on those formal representations. And then that led to a review paper that Jason was a co-author on that for me really crystallized how I see the field now today and going forward, and really crystallized, I think, because I was having a lot of like existential angst with LLMs and ChatGPT and all, like, what is my role? Is all of this solved? Was I wasting my time all this time? And Jason and his work really helped me see that there's still a place for the kind of stuff that we do. And really like what the benefits and the trade-offs are. And I think that's really exciting. And he's done other work besides. So he's been a really great student to have in the lab, a good citizen of the lab. He's mentored a lot of junior students. And I really appreciate all of your hard work and all that you've done. So let's thank Jason and welcome him. And then he's going to talk for about an hour, and then we'll do public questions, and then private questions, and then the committee meeting. And there's one small just note that George Konidaris is on the committee, and Jason had the most hardest thing for PhD students is to schedule the defense. And Jason had a difficult time doing that. I really appreciate all of the committee members' flexibility about this. And the thing that had to give is George couldn't be here. So George saw the talk earlier today or yesterday? Yesterday. Told me it was great, and has no concern. I shouldn't say that. But anyway, he told me it was great and he has no concerns. So George won't be present for the deliberations, but he's still on the committee. So thanks. Take it away, Jason.
Awesome. Hello, everyone. I'm Jason Liu. After many wonderful years at Brown, finally came to today doing my defense. So my research centered around connecting robots to humans through natural language. And today I'll talk about robotic language grounding, the first step towards developing robots that can use natural language. My research is driven by developing robots that assist people. So I imagine a future where personal assistant robots are universally accessible. And we would have a personal assistant robot in many homes. This video shows PR1 being teleoperated to perform many household chores, like vacuuming the floors and tidy up the living room. So how do we convey those complex tasks to robots? We have many interfaces. They each have their own pros and cons. So first, we have a graphical user interface, like a touch screen or VR. So they're very expressive and visual intuitive, but they're not very flexible. To command a robot to grasp something or go somewhere, we have to manually specify the right pose for the robot. And then we have code, which is very expressive, flexible, and ambiguous, but it requires expertise or training to use. And natural language is a great way for humans to communicate with robots. This image is actually taken from a real robot experiments. We can see we use natural language to specify a very complex command. So natural language is expressive, flexible, intuitive for a non-expert user to use. We humans use natural language to talk to each other all the time. So when we deploy robots in millions of houses, we would want to talk to robots just like we talk to another person. And with the advance of large language model and vision language models, we should be able to talk to robots just like we talk to other people. So language is a great interface for human-robot interaction, but how come we don't have a robot we can talk to at our homes? In other words, what are some of the challenges of using natural language? First, natural language is very complex. For example, I can give this command to robot, go to the store on Main Street, but only after visiting the Chase Bank. And after you enter the bookstore, move slightly to your left, find the orange magazine on the brown bookshelf in front of you. It's a very expressive natural language command that's complex. It specifies a long horizon spatial temporal task at different levels of granularity. From this example, we can also see natural language is compositional. So we can decompose this command to referring expression, for example, the bookstore on Main Street, or the orange magazine on the brown bookshelf in front of you, and the temporal patterns. So this kind of gave us some insights of how we could process the complex natural language command. I'm going to try to leverage this compositionality of natural language in my work. Almost all the natural language command we give to robot can be ambiguous. For example, if I tell the robot to go to the burger shop on Hope Street, there could be two burger shops, Harris and Chom's. So which one specifically do I want the robot to go to? Robot need to figure that out. And also there's a disconnect between the text space of natural language and the physical world that robot is in. So language must be grounded in the physical world. For example, I may ask the robot, can you fetch me the cup? Because the robot operates in the physical world, the natural language command we give to the robot should also be grounded in the physical world. And the problem of robotic language grounding try to address all of the challenges and many more. So because of those challenges, even with larger language models, the language grounding problem is still very hard. So for the rest of the talk, the definition I'm going to use for robotic language grounding is we want to map words in an utterance to robot's perception and action. For example, in this command, we would want to map the word cup to the green cylindrical object in front of it, and map the word fetch to the motion of moving toward this green cylindrical object. And to solve this problem, we want to answer three questions. First, what grounding representation to use? Second, how do we ground natural language to this representation of choice? And once we ground natural language to this grounding representation, how do we produce robot actions from it? And to kind of see how the field is answering the question, we did a survey paper, like Stephanie mentioned, in 2024. We reviewed and situated many robotic language grounding papers into a spectrum with two poles. On the left hand side, we have a language grounding word that ground natural language to symbols, discrete symbols. So those symbols contain a lot of structures. Thus, they have less variance of grounding natural language to those symbols. And they have unambiguous semantics, which provide verifiability and interpretability. And on the far right of the spectrum, we have continuous representations, which are high-dimensional embeddings. They have less structures, so they have more variance of how we can ground to those representations. But they're more adapted to new environments and new tasks. And as we build the spectrum from left to right, we can gradually reduce the structure in the grounding representation. In my thesis, we mostly focus on grounding natural language to a structured representation, in this case, formal language, which is very good at capture long horizon tasks and encode non-Markovian constraints. And because robot using this structure, it can perform understand many complex natural language commands. For example, spatiotemporal command like go to the white car near dumpster exactly 3 times. In addition, avoid stairs in front of the apartment. And also go to the wet desk, but only after the kitchen counter, fetch a delivery task. Those language commands are challenging because they specify long horizon tasks that requires temporal ordering of subtasks. And we want to deploy this language grounding system in novel environments without retraining on language data. Okay, so I'll first present 2 technical papers that ground natural language two structured representation. I already talked, besides the survey paper, we're going to talk about LAN to LTL, also LAN to LTL2. And once we ground language to the structured representation, we can explore this structured grounding representation to transfer learned skills to solve novel tasks in the same environments. And that brings us to the LTL-Transfer work. Okay, the first work I'm going to talk about is LAN to LTL, which ground temporal language in novel environments. The contribution of this work is we're grounding temporal navigation commands in novel indoor and outdoor environments without retraining on language data. So we open source a software package that enables users to unbox and command an autonomous drone in any cities provided semantic map and motion planner. And we tested language grounding system in 21 novel cities and deployed the robot in 2 indoor environments. And because we use this structured representation, the robot will be able to detect if the given command is infeasible and abort execution. Okay, so go back to the original question on language grounding. So what grounding representation we want to use? Perhaps we can think of some of the desired properties we want this representation to have. Because natural language is ambiguous, we want to ambiguously ground natural language to a structured representation. So we want this structure to have ambiguous semantics, which can ambiguously and precisely capture natural language. And we also want to preserve the expressivity of natural language. One of them is the temporal constraint natural language can encode. For example, go to the bookstore first, then the cafe, and always avoid downtown. Also, we want this structure be able to capture spatial constraint natural language may express. For example, put the fork on the left side of the plate. And because natural language is compositional, we would want this structure to also be compositional. So we can ground different part of natural language to different part of the structure, which inform us to maybe build a modular system that does the work. And because of compositionality, we can also, the compositionality would also help robots to reuse prior knowledge. And we also, because we deploy robots in human environments, we would also want this structure to provide safety guarantees. For example, we want this structure to enable robot to detect when the task is infeasible or execution violate the given constraints. So given all those desired properties, what is the good structure to use? Linear temporal logic, or LTL for short, actually capture a lot of those desired properties we want. It was invented by Bernoulli in 1970s. And a large number of papers have used this, a large number of natural language commands can be captured by LTL. So we want the structure to capture a large portion of natural language command. And the survey paper from 2019 surveyed 306 robotics papers and found that 245 task specification can be expressed in LTL. So I'll go through the one example to explain the semantics of LTL. So given this natural language command, go to the supermarket, but only after visiting bank. We want to ground this LTL to natural language to LTL formula, finally Walmart and not Walmart until Chase. And different part of the natural language ground to different part of the formula. For example, go to a supermarket is grounded to finally Walmart, but only after visiting the bank grounded to now Walmart until Chase. And once we have this LTL formula, we can translate that into a Bucci automata, which keep track of the task progress. So transition in the environment induces transition in this automata. So when the robot first started, we start with in the automata state 0. As robot move toward Chase Bank in the environment, the automata transition from state 0 to state 1. And as robot move towards Walmart, the automata transition from state 1 to the final state 2. Okay, so we decided to use LTL as a grounding representation. And how do we ground natural language to those LTL? I'm going to present 2 works, LAN to LTL and LAN to LTL2, which ground temporal language and spatial temporal language. Some of the assumptions I'm going to use in this talk is we assume the environment is static and fully observed, which means all the objects are stationary in the environment, and the robot knows the object location of the poses and its own location in the environment. And we also assume we're provided predefined proposition and then semantic information that describe them. For example, for the proposition of Walmart, it could be described by a stream of text. And also a proposition that described by image. For example, car 0 is described by this image of red car. And so formally define this line to LTL proper definition is in the input, the system takes as input the temporal navigation command and the semantic map. And we want the system to output an LTL formula whose propositions are grounded to real-world landmarks. For example, we can give this input command, go to the store on Main Street, but only after visiting the bank. And also the semantic map or database that encodes 3, using text to describe 3 propositions. But we want to output the grounded LTL formula, finally Walmart, and not Walmart until Chase. So how do we resolve, process this complex command? We leverage the compositionality of natural language. So first, we decompose natural language to the temporal patterns and the referring expressions. And we extract referring expressions from this natural language command, which are the store on Main Street and the bank. Referring expressions are noun phrases or proper names that refer to some landmarks in the environment. In this case, the store on Main Street would refer to the landmark Walmart, and the bank would refer to landmark Chase. And we use in-context learning with GPT-4 to do the recognition. So once we extract the referring expression, we want to ground them to the landmarks we just mentioned before. So how do we do that? Is we first using GPT-3 to convert the referring expression, the text, into text embeddings. Also use GPT-3 to convert the semantic information in text to a text embedding. And then we can choose the similarity between the text embedding to find the best match. In this case, the store on Main Street is best matched to Walmart, and the bank is best matched to Chase. Now we grounded the referring expression part of the natural language command. We're going to turn into the temporal part of the natural language command. So we replace the referring expression by symbols and to turn the input command to a lift command. So it becomes go to A, but only after visiting B. And then we can use the pre-trained large language model to translate the lifted command to lifted formula. In this case, find out A and not A until B, and replace the symbol A and B by the grounded propositions we grounded before. So, and then we get this grounded formula, find out the Walmart and not Walmart until Chase. And so this system is generalizable because it doesn't have to memorize all the different landmarks in different environments by lifting the command. So to test the generalization of this system, we develop a set of tests going from a simple task to a more challenging task. So first we have alternate holdouts. So during training, the robot has seen all types of formulas, but during tests we hold out specific natural language command associated with a particular formula. A slightly more challenging task would be during tests we hold out formulas of a novel number of propositions. So during tests, the robot has seen this type of formula, but during training, the robot has seen this type of formula, but during tests, it hasn't this number of proposition in this formula. And the most challenging task is we hold out entirely a complete set of formulas, may have complete new structure. So we evaluated our lifted translation module on this task. For alternate holdout, our fine-tuned model performs really well. And as we increase the level of generalizations, the pre-trained model actually gradually outperforms the fine-tuned model. Because we're putting as many stuff as possible in the pre-trained, in the fine-tuned data set, it limits the generalization to normal formulas. But for our use cases, we just put as many examples as possible into the fine-tune set. So for the full system evaluation, we deployed the language grounding system in 21 novel cities and tested on around 2,000 semantically diverse commands, and using average success rate as a performance metrics. So the previous state of our CopyNet, which is seek-to-seek GRU with attention, it doesn't perform really well in our test set. And also prompt pre-trained GPT-4 model could not solve the task. But with our modular approach, LAN to LTL, our system can get really outperforms the previous state of the art. We also deploy the same system we tested in simulation without modification for navigation tasks on the real robot. So here, robot need to visit the bookstore first and then visit the wooden desk twice, maybe to deliver a textbook. And provided with the semantic map and motion planner, the robot can solve this task. And then we tested the same system in 2 indoor environments to solve 48 navigation commands. 42 of them are successful execution, and 16 of those commands are infeasible, but the system will correctly aborted after it detects the infeasibility of the command. So we dive a little bit deep into the correctly aborting behavior of the robot. So given this contradictory command, go to the counter but never visit the counter, the robot will be able to detect this command is infeasible and never start executing. And for this command that have environment constraint, find the kitchen counter, in addition avoid the doorway. Maybe the doorway is the only way to get the kitchen counter. The system will be able to also detect this and never start acting. Some of the failure cases we observed in this experiment is if, let's say we fine-tuned the model, live translation model, to understand LTL formulas at most 5 propositions. If we ask the model to visit the counter at least 6 times, it would ground it to a syntactically incorrect formula because I haven't seen this type of formula. But the system was able to correctly detect the incorrect syntax and abort execution. Another challenge is when we give ambiguous command. For example, we may ask the robot to go to the couch, but there could be 2 different couches in the environment. So for this in this case, our system will just ground to an arbitrary couch. Leave this to and in the future works, I'm trying to address this challenge. Okay, just to summarize, for the LAN to LTL work, our contribution is grounding temporal navigation commands in novel indoor and outdoor environments without retraining on language data. And because we're using LTL as grounding representation, the robot will able to abort execution when they detect infeasible command. So the next work, we improve the LAN to LTL system by leveraging ground spatial temporal command by leveraging multimodal semantic information. So the contribution of this work is we're grounding spatial temporal navigation commands in novel indoor and outdoor environments without retraining on language data. The language data language command we're able to handle contains 47 temporal patterns and 19 spatial relations. And we're leveraging multimodal semantic information to describe the proposition in the environment. So the proper definition is very similar. So we're taking a spatial temporal navigation command instead of just temporal command. And the semantic map contains both textual description and image description of the propositions. We still want the system to output an LTL formula whose propositions are grounded to real-world landmarks. So one example is one running example will be visit this vegan restaurant west of the bakery, only then go to the red car to the right of the bakery. And in the semantic database, it contains 3 propositions. 2 of them are described by text. One of them is described by image. And we want the system to output a grounded formula, finally car 0 and now car 0 until Plant City. We leverage the same. We do the same thing, leveraging the compositionality of natural language and develop this modular system, which we use to first extract spatial referring expression from natural language command. In this case, and turn them into spatial predicates. So spatial referring expression are referring expressions connected by a spatial relation. In this case, the vegan restaurant west of bakery is turned into a west and the vegan restaurant and the bakery, the predicate, and it's mapped to the plant city west of bakery, plant city in this environment. And the red car to the right of bakery is mapped to the red car, and we turn the spatial referring expression into the red car and the bakery, the predicate. We use the same technique in concept learning to extract the spatial referring expression and then turn them into a spatial predicate. And once we extract the referring expression, we're going to ground those referring expression in the spatial predicate into landmark in the environments. We apply the similar technique, which is use text embedding to turn those referring expression into text embedding, and then we use VLM to turn the image into an image embedding, and use compositionality to find the best match between the embeddings. And in this case, the vegan restaurant is grounded to Plant City, the bakery is grounded to Wildflower, and the red car is grounded to Car Zero. And once we grounded the referring expression in the spatial predicate, we want to check if the grounded landmarks actually matches the spatial relation. To do that, we apply defined rules for each spatial relation. For example, for the spatial referring expression, the red car to the right of bakery, the red car, we draw two vectors, one from the bakery to the red car, and another one from the bakery to the robot. As long as the vector from the bakery, the red arrow going from Wildflower to the red car is on the right side of the green arrow, we know the grounded landmarks satisfy the spatial relation. And by using this module, we grounded the spatial referring expression to propositions, landmark propositions. And then we just grounded the spatial part of the command, and then we're gonna try to ground the temporal pattern in the commands. So we replace the spatial referring expression in the input command by symbols and turn them into the lifted symbol as we did before for the previous work. And then we use a fine-tuned large language model to turn the lifted command to lifted formula, and then replace the symbols in the lifted formula by the grounded proposition. And we did a comprehensive modular evaluation on each of the modules. For the spatial referring expression recognition module, where we extract the spatial referring expression and turn them into predicates, our module performed uniformly well in landmarks with increasing number of city with increased number of landmarks. For the referring expression grounding module, where we ground the referring expression to real landmark in the spatial predicate, we increased the number of landmarks in our testing cities, the top 1 accuracy of our module dropped, but the top 5 and top 10 accuracy is still uniformly high in all the cities. And that's what we need for the next module, the spatial predicate grounding module. It takes the top 10 candidates. As long as the correct grounding is in the candidates, it can correctly detect it. So we see the performance of the spatial predicate grounding module is uniformly performed uniformly well in cities with different number of landmarks. And for the lifted translation module, where we turn the lifted command into a lifted formula, our fine-tuned model still performed the best. But as we increase the number of examples in the prompt, the pre-trained large language model, GPT-4 in this case, have increased, the performance increased quite a bit. So which kind of shine the line of maybe a future work. We can, instead of fine-tune our own model, we can collect a large data set and then try to feed as much information as we can in the prompt. So we actually max out the context window at the 100 examples. To evaluate the full system, we did an abolition study. So in 4 different cities, on 20,000 semantically diverse command, still using average success rate as the performance measure. So a system only be able to process image doesn't perform quite well, and the system only be able to perform text have worse performance. But by leveraging the both image and text description of the landmark, our system vastly outperforms the ability system. And we also deploy the same system with a modification in indoor and outdoor environments. In this case, And so we ask the robot to go to the white car near the dumpster exactly 3 times. In addition, avoid the stairs in front of the apartment. So from the little map, we can see that there are 2 ways to get to the white car. One is go between the garage and the apartment. Because there's a stairs, there's a safety constraint. We ask the robot not to avoid the stairs, so the robot will be able to detect and avoid the path and go through the top path to the white car near the dumpster. And it would visit the dumpster 3 times to simulate maybe taking out the trash, a task of taking out the trash. Yeah, so we deployed the same system in indoor and outdoor environments to solve around 25 tasks, provide the robot with a semantic map of environment and the motion planner. To summarize this work, LAN to LTL2, our contributions are grounding spatial temporal navigation commands in novel indoor and outdoor environments without retraining on language data. We're able to ground spatial temporal language with 47 temporal patterns and 19 spatial relations by leveraging the multimodal semantic database. Okay, so in these 2 works, we answered 2 questions: what grounding representation to use, and how to ground language to this representation of choice. So next question I want to answer is, how do we produce robot action from this representation? And I'm going to answer that through the work we did, LTL-Transfer. The contribution of this work is we leverage the compositionality of this structural representation, linear temporal logic, to reuse learned policies to solve novel tasks. And because we reusing prior knowledge, the system doesn't have to learn policy from scratch for every new task. And the system will be able to abort execution if it detects the learned policies are not enough to solve a new task. A quick example to demonstrate how we reuse learned skills to solve new tasks zero shot. For example, we learn during training how to fetch a juice bottle and how to fetch a textbook. During test time, we want a robot to complete the task of fetch textbook first and then the juice bottle. We can sequence in together the skills we learn from the training task and solve this test task. And to formally define this problem, the system takes an input, a set of training LTL tasks and a novel test LTL task, and a set of predefined proposition of known landmarks. And we want the system to output a sequence of skills to solve this test task zero shot. This algorithm we developed has 3 steps. First, we learn state-centric skills. And then we decompose the state-centric skills to transition-centric skills. Last, we transfer the transition-centric skill to solve novel tasks zero shot. Note the state and transition mentioned here refers to the state and transition in the state machine, not in the environment. So for example, to demonstrate the learning phase, given this training task, finally juice and final desk, which means get the juice and go to desk in arbitrary order in a discrete environment. We first turn this LTL former into a state machine. We call the literature we call reward machine graph. The node in the reward machine encodes the task progression. In other words, some subtasks. And the edges are labeled by Boolean formulas. If satisfied, will progress the system to the next state of the reward machine. So to leverage the compositionality of this LTL formula, we decompose the given LTL task into subtasks encoded in the reward machine state 0, 1, and 2 first. Then we can use any RL algorithm compatible with solving LTL formula to learn a policy for each subtask. So we learn policies for state 0, 1, and 2. And the policy would tell the robot what action to take in every reward machine state. So the policy we learn for state 0 would tell the robot how to transition the reward machine from initial state 0 to state 1. To state 1 or 2 depends on the proximity of the robot to the object in the environment. Similarly, we would learn our policy encoded for reward machine encoded from the state encoded in reward machine state 1, and our policy from the state encoded in reward machine 2. Okay, once we learn the state-centric skills, we want to decompose them to transition-centric skills to target specific edge transition, which we're going to use to transfer later on. So to do that, we partition the state space based on the proximity of the robot to the objects. So for the skill we learned from state 0, we partition into we decompose it into a transition-centric skill that transitions the reward machine from state 0 to state 1, which reaches the desk. And also another transition-centric skill that transitions from state 0 to state 2 in the reward machine, which reaches the juice bottle first and then reaches the desk. Okay, so once we learn those portable skills, the transition-centric skills from the training task, given a new test task, how do we zero-shot to transfer to solve this task? We first look at each edge of the test task and see if we can matching edges in the training set. We find a matching edge, we just apply the skill we learned from the training task. In this case, from the first training task to a transition reward machine from state 0 to state 1 in the test task, which reaches the book. And then we look at the next transition in the reward machine, see if I can find a matching edge in the training task. In this case, we found an edge from the second training task, and we apply the corresponding skills, which transition the reward machine from state 1 to state 2, which reaches the desk. And then to evaluate our system, we compare with 3 baselines, LTL to action by Andrew et al., which encode LTL using neural networks, implicitly represent LTL formulas and implicitly try to do the transfer. LTL transfer, our work explicitly model the LTL formula and try to explicitly perform the transfer. And the LOPO, which is the submodule we use, by definition, it doesn't do transfer. It just learn how to solve a set of LTL tasks. And the random policy there for comparison. As we show, our system outperforms the baselines, especially for the hard tasks, which there could be failure states, which means robot may possible to validate safety constraints. And for those tasks, our robot will able to detect failures and never take a dangerous action. Some of the baselines wouldn't be able to detect those failures and would validate the safety constraints. And we deployed LTL transfer at the task planning level on quadruped mobile manipulator later. We learn policy from 20 training tasks and then transfer to 100 novel tasks in zero shot with 100% success rate. We demonstrated 50 of the test tasks, one here on physical robot. And about 1/3 of them are fetch and deliver tasks, and 2/3 of them are navigation tasks. Here, the robot need to go to the kitchen counter and then deliver the juice bottle to the desk. And during execution, robot will abort whenever the learn options are insufficient to solve the given task. Yeah, and we ran a number of robot. We deploy a number of we deploy robot on a number of tasks. Okay, so this part of work connect the structure to robot action. Our contribution is leveraging the compositionality of LTL task specification to reuse pre-learned policy to solve novel tasks. And the system can abort execution if it detects the learned skills are insufficient to solve the test task. So in my thesis, we talk about how we can ground natural language to a structured representation in this linear temporal logic. We published 3 papers. One is a survey paper. The second one is line to LTL, grounding temporal navigation command. The third one is line to LTL2, grounding spatial temporal navigation command. And once we have structure, we can leverage compositionality to produce robot action zero shot. And we published LTL-Transfer to solve this task. Some of the future work I'm looking forward to do is LTL is very good at capture long horizon tasks at the task level, but there are limitations of the natural language human can say to robots is limited by this grounding representation. Some of the low-level command, for example, move slightly to the right, or move too slightly in the front. LTL is not very good at capturing those. By using other structure, for example, code or high-dimensional embedding, we can capture natural language command at different level of granularity. I'm trying to have a hybrid structure that can capture the natural language command, more complex natural language command. We don't just use natural language to communicate with with robot. We can also use demonstrations or like vision. So the next work would be multimodal grounding to ground vision, language vision and demonstration to a structure, and which induce the robot action. And because natural language is ambiguous, for the future work, I'm really looking forward to do this human-robot dialogue paper, which we can have robot ask clarification, quantify the uncertainties, and have robot ask clarification questions to reduce the uncertainties, and to resolve the ambiguous natural language command. Yeah, so this will be my thesis and the future plan. And thanks so much for attending.
So for link to LTL2, how did you pick the 13 spatial propositions that you had in the system, and what are your thoughts about like how to use deep goo to learn them instead of manually defining them?
Yeah, so we kind of surveyed some of the papers doing robot navigation, and then find those are the spatial relations they used in their paper, and we also adding a few other things we thought about, think were interesting. So that's how we picked the spatial relations. For the deep goo part, instead of having this predefined, deep goo is very good at learning things on the fly.
Is deep goo a thing or just a phrase that you guys invented?
Vision language model. Vision language.
Okay.
Vision language model, like the foundation model.
Some of the names in the field now are very.
I was like, when you said deep goo, I was like, oh, this is like a Stephanieism, and now you keep using it. I'm like, oh, is there like a model called deep goo, like deep?
Because there very well could be.
There should be.
Yeah.
All right. Well,
But
next
no,
paper.
I just use it to refer to like large,
the
high
mystique
dimensional
of goo.
neural
Yes, of
models
course.
and,
Thanks. Thank you for
sort of
clarifying.
yeah.
We almost called our survey paper like deep goo.
But I said it was too mean.
What's that?
I thought it was too mean to put in the paper.
Oh, as like a title.
Yeah.
Deep goo.
So it's like a code name for the project.
Got it.
Yeah, so it's very good at detecting things not predefined. So a lot of limitation of our approach is we have to predefine a bunch of spatial predicates. So using deep goo can kind of detect all the a lot of spatial predicates on the fly, but it will lose some of the interpretability of it. So having a hybrid system that can detect things on the fly, but also encode some of the interpretability properties of the predefined things is something I'm trying to address in the future. Yes, Michael.
Since the room is asking questions. So the robot is so cool, right? The fact that you got it to do these things and it sort of marches around and it's just, just as a high level question, have you ever been tempted to engage the robot to solve a problem that you just needed solved, right? As opposed to in your research, you're like, oh, great, I have this thing. It can reach this item from the shelf for me, or like can fetch this. It can get me the remote that's sitting on the desk. Like, have you ever felt tempted to actually use it?
Like 4 hours later, you're watching.
Well, there's issues that might prevent you from doing that. But like, I'm just curious.
Yeah. So some of the work I really like is we can fetch books from bookshelf and deliver to the desk. That's something I attempted to use, and also the system is not there yet to do the real time. Like Ali said, it may take a long time. Latency might be high, but with some of the future work, we can ground language to different level of granularity. I'll use multimodal grounding is something we can improve system to one day we can deploy it in the real world.
Can you explain like how you actually ground this LTL into real world motor commands, like motor skills? For example,
Yes.
fetch book from the bookshelf, how do you really like execute this command? And for the navigation, like visit dumpsters 3 times, how you actually implement this real world experience?
Yes. So the language grounding work ground natural language to a structured representation LTL in this case, and then we use off-the-shelf motion planner to plan waypoints, taking this LTL as task specification and plan waypoints for the robot to execute. And then we have off-the-shelf controller to go through those waypoints. And for the manipulation task, we just predefined set a heuristic. Whenever we reach this location, if it detects a book, it's to pick it up.
Okay, so you have some, like, I guess, like heuristic or design like primitive to just fetch the book.
Exactly.
I see.
So yes. So for future work, looking forward to do a mobile manipulation tasks. Instead of predefined, we have more authentic way of combine the navigation and the manipulation. Instead of predefined heuristic at the location to execute it.
Makes sense.
Harold.
So I think I've asked you variants of this question before, but let me try a different version. Like in this whole process, you gather, like you take this like vague description from a human, and then you do a whole lot of work to disambiguate it and to fill in all of these details, and then the robot just goes off and does something.
Yes.
And it seems like there's something you could insert in the middle where you kind of report back to the human what you were going to do, like confirm that it's right or like check it somehow.
Exactly. So one thing some of the perform some unsafe behavior, for example. So one thing we try to catch that is robot on its own just detect infeasible tasks or infeasible behaviors. That's one thing. And then the future work of human-robot dialogue is try to address that issue of having this feedback loop from robot to human using natural language or some of the graphical interface. You can demonstrate, oh, this is the behavior I want to take. Should I proceed?
Yeah, so like I'm more interested in the infeasible behavior, and you've told me how that works, and that's very cool,
Yeah.
and I get that. Yeah, it's the ambiguous, or even when it's not necessarily ambiguous, but when the human has said something wrong,
Yeah.
when the LTL looks wrong, like
Exactly.
so you kind of see this as like a natural language loop, or is there some format that you can?
Yeah, it would be first it would be iterative process. I think we could apply something from a method program synthesis to correct this incorrect LTL formula. So 2 errors we've seen: one is syntactically incorrect LTLs, and then semantically incorrect LTLs. So the future work I'll try to address both of them. Yeah, so natural language is one way to interface between robots and humans, but there could be other like interfaces. Yeah, for example, if you put on a VR set, you can visualize how robots execute.
Eric, on Zoom?
Yeah, Jason, great talk. I was just kind of wondering if you could talk a little about dealing with uncertainty over the semantic map and ways of like dealing with that.
Uncertainty in the semantic map. So so we assume robots fully observe the environments. For future, so there could be uncertainty in the language. There could also be uncertainty in the environments. I think we can have a belief state of represent where all the objects are, and then factor the observation model of not have a perfect object detector, but factor in the using the confidence object detection model to update the belief of the objects in the environment. Yeah, Ali.
Cool, thank you.
Yeah, I guess because mine was kind of related to Rob's question. So yeah, you mentioned this, and I guess Tarek. So you mentioned that it could detect if there is like a inconsistency either directly from the logical form, like go downtown and don't go downtown or something. But then you also said like if there's one in the environment, like an inconsistency in the environment, so the only way to the fridge is through the certain door or something.
Yeah. So
can you say more about how that process works and what assumptions you have to make in order to
Yes.
place that guarantee? And then
Exactly.
we had a follow-up question.
Great
but
question.
first
So once we get LTL formula, we feed LTL formula and the semantic map, a topological map into a planner. The planner would output nothing in 2 cases. One is LTL is false. That means there's an infeasible task. Another one is it cannot find a path to satisfy LTL formula in the topological map. So the second behavior would catch the environmental constraints. And also,
Yeah, so this is with the complete observability, because you can imagine in some cases that the contradiction or the inability to complete the action wouldn't reveal itself until the robot starts doing stuff.
Yes.
And then it's like, oh, there's actually no safe way to do this. Like, does the system allow that, or can you imagine, like, what would you need to do to support that kind of recognizing those inconsistencies, or does this, is it not naturally compatible with what you're doing?
Yeah, it's a great question. So currently, the system would output the best things, like maybe the best LTL formula, the best action. So having probability distribution over possible LTLs or possible objects in the environment can help us resolve this ambiguity. So that's some of the future work I'm trying to address. So that could also induce the question asking behavior. So we want to
I was picturing not even like an ambiguity, but something like that person says, like, don't like, especially you can imagine a lot of safety violations and things will happen not really as a function of the map, but like as a function of what the robot needs to do to complete the thing. So it's like, okay, now it goes in and it opens up a cabinet and starts trying to take stuff down, and there's really no good way to get all the things down, safety, whatever.
Yep.
So these could be like constraints that would reveal themselves, and it's like at that point it's already, it's already midway through. It's already started executing a plan. This seems like in particular, trust issue, because the person has thought that in the past the robot said, sorry, I can't do that, it's unsafe. So they've expected when it starts going that thing must be safe, and now it's midway through and it's like, oh, actually it's unsafe. Right? Like, is this the kind of thing that fits into this framework at all, or does it require a completely different technical approach?
I think it fits in the framework, but instead of each module output the best answer at each module, we want to output distribution over things. And then when the uncertainty is high, that's when we want to inform the human, or either this task is infeasible or I need to ask clarification questions. So I think on the implementation level, we want the system to output distribution over possible things. Like, for example, trajectories. Yeah. And I think maybe just relate to some of the human behaviors. Sometimes when we start performing tasks and then we realize we can't do it. So so I think communicate that to human in a interpretable and transparent way is can help with trust stuff.
It's really interesting. I mean, I feel like this is just a really hard problem, especially just picturing from the user experience viewpoint. It's like, to us, it's really clear that like the kind of safety violation that might be recognized in the deep goo vision model will just have a whole different error handling case than the one that's like a function of this logical form in the semantic map. But the user doesn't know that, and they won't understand why sometimes they got a flag and it failed to do it, and other times it just proceeded to try to jam something that was too big through the doorway and smashed everything along the way, right? Like, and you're just like, well, that was because that was the visual model, but this one was the LTL, and they're just like, I hate this product, right? Like, you're just like, interesting, right? So it's just like this weird kind of, world to be navigating, where they might arise from all these technically very different types of systems, but to the user, especially if it's coming across in natural language, it seems like it's all just one thing.
Yeah.
Right, it's just the robot talking to you.
Yeah, my answer to that, we probably want to tell robot the subtask, robot want to tell human the subtask they cannot perform, and then maybe relate the reason why I cannot perform. Maybe something like, I cannot pick out this red jar in the cabinet because I couldn't find a way to stick my hand into it. Things like, yeah, exactly. Yeah. So instead of just shield the user from understand all the black box stuff, but tell them the things you cannot do and why you can't do.
Right. You have another Zoom.
Hey, Andrew.
Hey, Jason. Really great work here, and excellent presentation. Congratulations in advance. But I'm curious to hear your thoughts on sort of like the role of LTL and these more modular approaches, I guess, to these general purpose robots. And I'm curious what you think about that in the context of how people are currently trying to build these more general purpose robots through more and more like data driven in as an end-to-end way as possible. You know what I mean? Like
VLA stuff. Yeah.
Sorry?
Vision language action stuff.
Yeah, exactly. Like VLAs. So I'm curious if you think is there going to be like a sort of a regression back towards these more modular approaches, like having LTL in the middle. So what are just your thoughts for the future, I guess?
Yeah. So I think thank you for the question, Andrew. Thank you for zooming in today. Andrew is actually one of the author for one of the baselines we tested on. LTL to action. So what I'm thinking is, so we already see a kind of a trend of not just do end-to-end, but also have a more modular and hierarchical approach. I think that's the so to step back. So a few years ago, we've seen a lot of end-to-end approach came up, and even now vision language action models. But more recently, we started seeing hierarchical and modular approach becomes more produce more performant systems. So I think having a modular system provide the many advantages of we can reuse some of the modules, or we can replace some of the modules once we have more better subsystems. And regarding LTLs, I think LTL by itself is very contrived. So the natural language we can handle is kind of constrained. But if we can combine LTL with other structured representations, I think that can help make the language grounding system more robust or more flexible. So instead of having predefined predicates, we can also maybe have embeddings for different objects, for example.
Yeah, I noticed you had you included things like spatial predicates as well in the Lang to LTL2 work, which I thought was really cool. That was something that sort of extends beyond the work that we've done in our group, where we usually just consider like these atomic propositions, right? Yeah, so really great work again. Thanks for answering my question.
Thank you, Andrew.
How many API calls do you need to do for each, and roughly how much is that?
For each inference is not that much, under maybe like $1. But the evaluation we did, because we evaluated on thousands, tens of thousands of commands, so that adds up a lot. So that's what I try to do, is having a local, very capable open source model locally, instead of query large language model in the cloud.